Namaste and a very good morning to all of you. In today's presentation, we'll be talking about how to remove the problem of multicollinearity, how to rectify the problem of multicollinearity if your data has this particular problem called multicollinearity. We'll be looking at a couple of strategies to remove the problem of multicollinearity and to talk about how we rectify the problem of multicollinearity. I will be using the data set called as car sales. This is my SPSS screen. I will click on File menu, Recently Used Data. The file that I have is car sales. So this is the data set that I have. You're already familiar with this data set because it has information about different manufacturers and models of the vehicle. And then you have some other information about what is the sales value, resale value, type, price, engine size, horsepower, wheelbase, width, length. And if I scroll further right, you see variables like curb weight, fuel capacity, mileage per gallon, and you have the log transformed sales. I'll be taking this video in two parts. In the first part, I will show you how traditional regression works. And in the second part, I will specify what are the problems of traditional multiple linear regression. To show you part one, which is how traditional linear regression works, let me click on the option Analyze. Go to Regression. There are different types of regression that SPSS offers. I will choose the second option here called as Linear Regression. Once I click on linear regression, a new dialog box pops up. The dependent variable here would be sales, but we know that sales is not normally distributed, and therefore I will choose log transformed sales simply because log transformed sales follows normal distribution, and linear regression works best when the dependent variable is normally distributed. When it comes to the independent variables, I can choose all the variables apart from sales. All these are variables related to vehicle characteristics, which I will be choosing as the independent list. The method here is enter method. Please remember, this is the enter method, which generates the coefficients for all these variables that we have supplied. I've got 3, 3 plus 3, 6, 7, 8, 9, 10, 11. I've taken 11 variables. So for each of these 11 variables, you will be able to see the coefficients along with their significance value when you choose the enter method. Let me draw your attention to the right-hand side top corner. You have what is called as the statistics tab. I will click on the statistics tab. A new dialog box pops up. Here, I will be choosing two important options. First, what is called as the part and partial correlations. And the second one, what is called as Collinearity Diagnostics. Why am I clicking this particular option? I'm choosing these particular options because I want to detect the problem of multicollinearity in this data set. If there is multicollinearity, Collinearity Diagnostics will highlight the problem of multicollinearity. With these settings, let me choose the option Continue. My dependent variable is ready. I've got my independent variables. I've chosen the enter method. And by going to statistics, I've chosen part and partial correlations and Collinearity Diagnostics. Continue, and then OK. At a very high level, you can see some of the initial level of output. SPSS shows all the variables that we have taken in the independent list. What is the dependent variable is highlighted here as log transformed sales. R square value is 0.426, which is around 42%. And is that significant? Yes, the ANOVA table says that it is significant because the p-value is 0.000, which is less than 0.05, indicating that yes, this model is quite significant. We are able to see the coefficient values for each of the 11 variables that we have entered. This is not the focus of today's discussion. what is the focus of today's discussion? The focus of today's discussion is VIF. As you can see here, there are many variables for which VIF is greater than 4. 4 is the cutoff. If the VIF value is greater than 4, it indicates the problem of multicollinearity. If VIF is bigger than 10, it means serious multicollinearity. I can see there are at least 3 variables which have a VIF greater than 4. This is 18.94. If I scroll to the left side, you can see 4-year resale value, similarly 26.19. This corresponds to the variable price. And nextly, what you have is 11.27. This is for the variable horsepower. All these variables are causing high degree of multicollinearity. Further, when you look at the Collinearity Diagnostics, you can see the conditional index. A lot of these values are bigger than 15, indicating that there is a serious problem of multicollinearity in this data set. Now that we have come to the conclusion that there is multicollinearity in the data set, the question is, how do we remove the problem of multicollinearity? This is where we move on to part 2. Let me come back to the data set. As you can see here, these 11 variables that I have are my original variables. What I will do is I will standardize these variables. How do we standardize these variables? Let me choose analyze. The second option is descriptive statistics. And here, the second item is descriptives. Let me click on the option descriptives. A new dialog box pops up. You can see all the independent variables along with the dependent variable. I'll choose only the independent variables and push them inside the variables list. So these are the 11 variables that I'm interested in. And at the bottom left-hand side corner, you see an option which says save standardized values as variables. I repeat, save standardized values as variables. What this does is for each variable, it subtracts the mean and divides it by the respective standard deviation. So we are going to generate the Z scores. These standardized variables will be then used as the independent variables, not the original variables. I'm not going to use the raw data. I'm not going to use the original variables. I am going to derive the standardized variables or the Z scores and use the Z scores of each of these variables as the independent variables in my regression model. Let me click on OK. Now, the moment you click on OK, SPSS takes you to the output window and it gives you descriptive statistics. I'm not interested in these columns. So let me go to my data set. Let me scroll to the extreme right side. As you see here, there are new variables that are created. It begins with the prefix Z. These are my Z scores. So the Z score for resale variable is generated. Z for type is shown. The Z scores for price, engine size, horsepower, wheelbase, width, length, curb weight, fuel capacity, and mileage per gallon are shown. What I intend to do now is I want to use these new variables. These are the derived variables. These are my Z scores for each of the 11 variables. I want to use these new variables as the independent variables. Let me go to Analyze menu. I will choose the option Regression. Here, under Regression, I will choose the second option, Linear. Remember, these are all my original variables that I had chosen. I will select all my original variables, kick them out. I will choose the newly created Z scores or the standardized scores for each of my independent variables and push them in the independent list. This is the first change that I will be making. I am not building this regression model on the independent variables. I am building them on the Z scores. The second thing that I will be doing here is when it comes to method, the default method is enter. I will be clicking on the drop down menu and I will choose the method which is called as stepwise method. You also have remove method, backward elimination method, and forward selection method. I will not be explaining these variable selection methods in this video. As of now, let me choose one of the most important variable selection methods, which is called as stepwise method. As you can observe here, there are two things that I have done. One is basically look at the Z scores, and then I will be choosing a variable selection method called as stepwise method. What is this stepwise method? The stepwise method, at each step, the independent variables not in the equation that has the smallest probability of F is entered. I repeat, the independent variable which is not in the equation, which has the smallest probability of F is entered. Variables already in the regression equation are removed if their probability of F becomes sufficiently large. This method ends if no more variables are eligible for inclusion or removal. So stepwise method, as the name itself suggests, in each step, it enters that variable in the system of regression equation, which has the smallest probability of F. So this is what I will be doing. So I will be working on the Z scores and the stepwise method because the original variables have serious problem of multicollinearity. Now, this is the strategy that we have. I will go to Statistics tab. In the Statistics tab dialog box, as before, I have clicked on the option of part and partial correlations. Also, I have chosen the option of Collinearity Diagnostics. I will click on Continue and then choose the option OK. This is the output of stepwise regression method. Please observe variables entered. Here, stepwise method has chosen 4-year resale value as the most important variable. This is considered to be the most important variable. This is the one which is considered to build the model. And in the second step, wheelbase is chosen as the next important predictor. So in 2 steps, stepwise method has identified the best 2 independent variables, which is resale value and wheelbase. Look at the model summary. When we have built model 1, or look at the description given below, model 1 has been built only with the resale value. R square is around 27%. When I include resale value as well as wheelbase, that is 2 independent variables, R square jumps from 27% to 36%. So the final R square value here is 36.9%. Is this significant? When I look at the ANOVA table, I'm getting a p-value for the final model, which is 0.000. 0.000 is clearly less than 0.05. And since this value is less than 0.05, I will conclude that this model is significant. Let me scroll down. You look at the coefficients table. What was the coefficient table? How did the coefficient table look like before? This is with the entire data set. When we use the entire 11 variables list. So when we chose all the 11 variables as the independent variables, you could see that corresponding to each variable, we got the significance level. We also got the VIF. Please recall that the VIF values were very, very high. Now, when I look at the new table with the Z scores, please observe the collinearity diagnostics. These are the excluded variables. So I don't have to look at the excluded variables. Let me just look at the final coefficients table. Here, when I look at the VIF table for the final model, this is model 2. Please focus just on model 2. The VIF is less than 4, which is a comforting sign, which is very, very important, because if the VIF is smaller than 4, it means that there is no multicollinearity in the data set. Similarly, when I look at wheelbase, again, the VIF value is smaller than 4, indicating that the final model, when I build using resale value and wheelbase, the VIF value is less than 4, and therefore we have been able to reduce the problem of multicollinearity. The tolerance value is 0.997 here, and because the tolerance value is close to 1, this again is an indication that the variables are more or less uncorrelated. Let me scroll further down. This is the excluded list. I don't have to look at the excluded list. Let me scroll further down to investigate the collinearity diagnostics. Eigenvalue here is close to 1, which is a heartening sign, because when the eigenvalue is close to 1, it means that the variables are independent. Conditional index greater than 15 is an indicator of multicollinearity. Here, when I look at the conditional index has reduced to less than 15. So all these are bright signs. Conditional index less than 15, eigenvalue closer to 1, tolerance value closer to 1, VIF smaller than 4 are all indications that we have successfully wiped out multicollinearity from our data set. So this is a very, very simple strategy of using the Z scores and then running a stepwise regression method to only arrive at the most important variables. Now, one of the problems here is about R square. Let me just scroll up. R square that I am getting is 0.369. More than R square, many times what happens is adjusted R square is better when we are looking at model comparison. Let me look at the earlier model when I had all the variables. Look at the R square value. When I built the first model using the raw data of fuel efficiency, resale value, so on and so forth, R square was 42%, but the adjusted R square was 36.6%. R square will always be on the higher side, though you have insignificant variables. Insignificant variables do not contribute to the model, and therefore R square value will always be on the higher side, even though you have many useless variables. When you want to compare the performance of two models, please don't look at R square, look at adjusted R square to compare the performance between two models. In the first model, the adjusted R square was 36.6%. In the second model, which we have built after standardizing the variables, please look at the R square value. It is 35.8, which is very, very close to the earlier model. Here, I'm building the model with only 2 variables, unlike the first instance wherein I built the model with 11 variables. So it only goes to show that I'm able to explain 35% of the variables merely by using 2 variables, that is wheelbase and the second variable being resale value. So just by using the resale value variable and wheelbase, I'm able to explain 35.8% of the variability. So to summarize the discussion that we have had today, we detected multicollinearity with the raw data as a strategy to remove the problem of, to remove multicollinearity from our data set. We used the standardized variables, we generated the Z scores, and we ran the stepwise regression method, which is a variable selection method. It selects the variables or removes the variables based on the probability of F value. So this combination of using Z scores and stepwise regression method is a great strategy to remove the problem of multicollinearity. With this, I have come to the end of today's presentation. I request you to subscribe to my channel and share this particular video with your friends and relatives. I'll see you in my next video. Thank you very much.